Hi everyone, my name is Surya Ambati. Today we are diving into two super cool concepts. One is stochastic differential equation, shortly SDE, and another one is Brownian motion. Don't worry if these two concepts sounds fancy. They are just way to model the things that wiggles randomly like stock prices or dust particle in a water. Let me write those concepts on my screen. We are going to discuss SDE shortly, which is stochastic differential equation. Please forgive me, my writing is not that good. And another one is Brownian motion. We'll discuss where Brownian motion comes in stochastic differential equation. Yeah, before go further, I want to share these videos are unedited videos, so you may find huge pauses in between the videos. Please bear with me. By end of the video, you will understand what are these two concepts, stochastic differential equation and Brownian motion, and where this Brownian motion comes in SDE equation, and how they works. And I'll walk you through these two concepts with its features along with numerical examples. Let's get started. First, we'll see what is SDE and how mathematical equation it looks like. Let me write it down. SDE basically is a mathematical equation which used to model system that evolve over time with both deterministic and random components. Let me write it. SDE is a stochastic differential equation that is a mathematical equation to model systems that evolve over time with both deterministic and random component. Let me write it down how mathematical equation looks like for SDE. So SDE basically it describes that how quantity, here the quantity is x of t, changes over time when influenced by both deterministic part and stochastic part. So d of xt, a of, so here like I mentioned, xt is the quantity of change that we are trying to measure, and this is the deterministic part first, and this is stochastic part. So this is the deterministic part component, and this is random component. So in this random component, again, we have three subcomponents. Those are volatility and quantity of change xt and dwt. This dwt is called noise, and this is modeled by Brownian motion. This is where we see Brownian motion comes into the picture. This is the volatility, and this is quantity of change that we are looking for. So these are the three subcomponents that we can find it in random component. So stochastic difference, it is difference than the ordinary differential equation. So deterministic component majorly describes that ordinary differential equation. If I want to give an example, let's take an example of x squared. And if you want to understand, differentiate with the x, means we want to see how this specific, quantity is changing, x square is changing when x is changes. So differentiate of x square is 2x. I want to see what happens if x changes or x reaches to 3. So if I simply insert this 3 value inside the 2x, so 2 into 3, which is 6. So I can say that, uh, it is the quantity when x changes to 3, then the quantity is changing to the 6. That is how I can simply, uh, by using the differentiation, I can explain the changes in the equation of x squared. But this is the deterministic component, whereas we also incorporated few more components like volatility and change of a quantity change and dWt, which is a Brownian motion. So by combining all this, then we can say this is a SDE equation, stochastic differential equation. I'll explain this further with using few more examples. But for time being, you just imagine this is a volatility. It's like a volume knob, which increases or decreases the noise. The major reason that we use volatility, or the reason to introduce the volatility inside the SDE, is like it adjusts the magnitude of Brownian motion wiggles. In general, Brownian motion, ideally for modeling the natural randomness, like helps to model the natural randoms like stock prices, wiggles, or particle motions. But whereas in real time, the volatility stocks wiggles more than the stable one. So that's why we introduce this. I mean, they're also using the volatility inside the SDE equation. That is the reason. So let's move to the concept Brownian motion now, and we'll see what is the definition of Brownian motion and what are the features it has. And I'll explain with examples, and also I'll try to explain with graphical way that how this Brownian motion changes or how it is modeled with the simple examples. Let me write it down on the screen now. Brownian motion. So this Brownian motion is also called as a linear process. Linear process. The physical phenomena, or the random movement of particles, was observed by Robert Brown in 1827. However, the famous mathematician Norbert Wiener gave the rigorous mathematical foundation. He gave this formal definition for Brownian motion in 1923. Let me write it on those 2 points as well. Physical phenomenon was observed by, I don't know why my pen is making some issue, by Robert Brown in 1827. However, the formal mathematical definition to Brownian motion was given by Norbert Wiener in 1923. So first we'll discuss the definition of Brownian motion now. Then I'll explain few of the main key features for Brownian motion. So Brownian motion is a way to model random or continuous movements, like jittery path of a dust particle in water, or unpredictable wiggles of stock prices. So I'll give you one basic or layman example. Imagine a drunk person stumbling randomly, and he takes a small and random steps, either left or right. So the probability of taking the left or right is 50-50 chance. So after certain time, this path looks like jagged or unpredictable. So Brownian motion comes into the picture and it helps to model, the randomness or the path of jagged or unpredictable, which was taken. Uh, so that is why we use a Brownian motion. And the key features of Brownian motions are like random wiggles, are continuous, no memory, or spread over time. So I'll explain one by one. Let me write it down on my screen. Key features are random wiggles, continuous, no memory, spread over time. So what this random wiggles is like, uh, at each moment, it moves either up or down randomly. And second key feature of Brownian motions is like it is a continuous, which meaning like there is a no sudden jump in the graph. That if you see even stock price graph, then there is a continuous and connected with each point. There is a no sudden jumps. Like if I want me to example, it moves like this, and suddenly there is a no gap, and it won't move that in that way. It is a continuous. That is what I meant. And also, even though it is continuous, it is not smooth. It won't move smoothly like this. It is a jittery. It is more like it moves like this. So that is what the future of the Brownian motion. That is what we are going to model it. And the third one is a no memory, which means like each step. I mean, first step is independent to the next step or previous step. It won't remember the last step. It may be down or it may be go up. Anything happen. So that is what the another feature. And finally, spread over time. The farther we go in a time, the more spread out the path can be. So let me explain these where these features comes into the properties of a Brownian motion, and also I'll explain with one of a numerical example so that you can understand it a better way. So first, the Brownian motion, try to model for the continuous time, random, even though I'm saying that it is in a random work, but it is in a continuous time. So first I will explain how we can define or how we can find out the Brownian motion for discrete random variable. Then how this discrete random variable converts into the continuous. I'll explain with examples. Let me write it down. So first I told, right, I'll explain discrete random variable. To find out, Brownian motion, basically we need or we have to understand these three properties. One is the mean of random walk is always 0. I'll explain why. A property of Brownian motion is mean of total position is 0 or expected position.